Size exclusion chromatography lets us separate proteins by size, either to purify or analyze. But of all the types of protein chromatography that you might be using, size exclusion tends to cause the most confusion. This is because the bigger proteins travel faster, which is like opposite that you would see when you did something like an SDS-PAGE. And this is because the bigger proteins get to take like shortcuts. So these columns are filled with these little beads called resin. And unlike the beads in other types of columns that we typically use, the proteins aren't actually sticking to the beads. Instead, they're just moving through and around them. I say through because these beads are actually little gel beads, and they have all these pores. The bigger proteins are too big to get into all of those pores, so they get to just kind of like go around them. Whereas the little ones, the little proteins and the salts and that sort of thing, they get trapped into all of these pores, which I show them as tunnels, but they're kind of like dead ends. So the little guys, like, they have to go in because they're just like moving randomly around, they're moving down, then they get sidetracked and they go into this little tunnel, but it's a dead end, so then they have to come back out. So basically the little guys are traveling further to get through the column, so they're going to travel slower. And so that means that they're going to take longer to go through, and they're going to elute or come out of the column later. So if you were to look at a chromatogram, then the little guys would be further to the right, so at a higher elution volume or time. You can see the scale, the x-axis can be like in time or in elution volume. So the difference is, there are also different types of columns. So we can do things like, if we want to purify a protein, we'll use a bigger column. And so the bigger column is not because it's bigger proteins, it's because you have more sample that you want to load. So this is like a high load column. I used one of these yesterday because I had oodles of protein. It was awesome. But today I have a different protein, and I'm using the smaller column because I don't have quite as much protein. If I had a little tiny bit, I would use this analytical column. But the volumes that you run through here aren't really enough to do much with. To see, like, if a protein's really pure, you should have a nice sharp peak, and importantly, you can see if the proteins are interacting. So a smaller protein is going to run really slow. But if it's bound to a bigger protein, now it's going to run really fast, and so you can see the shift and the peaks to see if things are interacting. So this is a form of analytical size exclusion chromatography. So today I'm going to tell you a little more about the theory as well as some practical things, like how we actually run these columns and how we choose between the columns.
So size exclusion chromatography is one of many forms of protein chromatography. And so I have a lot of posts on the other types, as well as a whole page on my blog with a bunch of links to posts that I've done on these various topics. So if you want to learn more about these other types, like affinity chromatography or ion exchange chromatography, then I will direct you to links for those. But today we're going to talk about this size exclusion chromatography. And so, as I mentioned before, there are kind of these two main flavors of size exclusion chromatography. There's preparative, where your goal is to doing it as part of a purification and you want to isolate and keep pure protein. And then another type is analytical size exclusion chromatography, where you're trying to basically see if proteins stably bind each other. You can also do this if you want to check for degradation of your protein or some sort of aggregation, dimerization, various things like that. And with that, you're just taking smaller samples and you're doing it basically just to get a look. And we'll talk more about these differences in a minute. But the version that I'm typically doing it is I'm doing it as part of a preparative size exclusion chromatography. And so I'm actually doing it at the end of a series of chromatography runs. So my workflow commonly goes like this. I take my protein and I express it recombinantly. So I express it with a tag, and then I use this tag in affinity chromatography to bind to this resin binds to the tag, and then I compete things off. Then I separate things by charge. And now finally, my protein's mostly pure, but I want to use the size exclusion chromatography to get it truly pure. And also it's really good for buffer exchange. So basically what my protein comes in with, doesn't matter. It's going to come out in what was in the beads. And so it's going to come out in whatever you equilibrated your column in. And so this is a convenient alternative to something like dialysis, where you're basically sticking your protein in a bath of liquid and then waiting for the liquid for stuff to diffuse and then changing the bath water and doing it over and over. And that can that can be a pain. And so this is an alternative, but you do have to concentrate it first. But the benefit is that you're going to get a purer protein. And so we'll talk more about this as well. How it works is you're going to inject your protein into this injection port. And so before you do this, you're going to concentrate your protein down. You want to concentrate your protein down as much as you can, kind of without your protein crashing out. So if you concentrate your protein too much, then it might precipitate out. And so proteins don't like to be at too high of a concentration. The limit is going to be different for different proteins. And so you might need to test with your protein of interest to make sure that it's not going to precipitate out. You also want to make sure that it doesn't get too viscous. If it gets too viscous, it's going to cause problems with the pressure on the column. But you want to choose a smaller volume, because what's going to happen is that when your things are entering the column, when you inject it, they're going into the sample loop I'll tell you more about, and then they're kind of going to get held there until it's their turn to go onto the column. When they go onto the column, now they're just going to separate based on how they travel through this column. And so you want them all to kind of get to the head of the column at the same point. It's kind of like why we use stacking gel in an SDS-PAGE gel, so that all of the proteins, we kind of get them to the starting point at the same time. There's no stacking gel in a size exclusion chromatography. So we need to make sure that the way that we get all of the proteins to the start at the same time is by using a small volume. So that if you can imagine, if you had a large volume, then things that were injected last would have a big gap from the things that were injected first. When your protein's going through the column, so you've injected it, you move it onto the column, and now it's going to face this situation. I like to think of it kind of like a bunch of different tunnels through the beads. The beads, I'll show you more in this handbook later, but the size exclusion chromatography handbook from Cytiva is really, really great. I don't work for them or anything. They just make the ACTA and all the columns and stuff that I use, and they have some really nice resources. This is an electron micrograph of what the beads actually look like inside. So you can see there's like all this porous. So it's like this porous network, and the little things are kind of they wander through, and then so it takes them longer. When they're traveling through the beads, they're going to be coming in and out of these various pores. Whereas the big guys, they can't get through all those little guys, so they're not going to wander as far. And so they're going to travel more quickly. You can think of this as kind of like if there are tunnels with clearance heights, then the big trucks can't go through the tunnels, but the little guys, they go through the tunnels. And so they're going to take a longer journey through the column. So now imagine what's going to happen when your protein is going through the column. The big things are going to go through fewer tunnels. The little things are going to travel through more tunnels. Because they're doing this and they're going into these tunnels and they're getting like dead-ended and they're wandering around, they're going to travel longer. So the actual distance that they're traveling through these columns, even though we have the column height, so we have that column height was like 200 millimeters, or that column height was like 600 millimeters. But the actual distance that these molecules are traveling is going to depend on how much of the pore volumes that they have access to, which is going to depend on their size. The bigger things are going to go through fewer of those tunnels, and they're going to travel faster. So when you look and see where they elute, where they come out of the column, it'll be sooner than a little protein, which had to go through all of these different tunnels, and therefore it is going to elute later. If you had salts and that sort of thing, they're going to go through all of these. And so your protein is going to come out way before your salts do. And so this is why your protein is coming out with the buffer that you equilibrated the column with, so that you filled all those pores with beforehand. And this is why we can use it for buffer exchange, and why our proteins are going to come out way before that other stuff. At the end, you typically often see like a peak that doesn't correspond to any protein. It's just like a bunch of salts and stuff coming out. And so it might confuse you. You're like, why is there this peak? And then you run a gel and there's like nothing there. And you're like, oh, it's probably the salts and stuff. This is the idea with when you're doing any type of size exclusion, is that you have this relationship between the size and the elution volume. You should note though that the size, when we say size, this is referring to typically the ranges are given for things like based on their like relative molecular weight, so like how many amino acids they have. But the pores don't really care how many amino acids you have. They care like how big you are, and how big you are is not necessarily how many amino acids you are, because proteins, what it actually depends on is the hydrodynamic radius and stuff. So it assumes that your proteins are all like the same, like perfect spheres and stuff, but your protein is not going to be a perfect sphere. Your protein might be more floppy and it might be more different things. And so, for example, there's this protein that I purified last week and it's only like 40 kilodaltons, but it runs like it's like 100 because it's very flexible and dynamic. And so it's going to have a harder time getting into those tiny little pores, even though it doesn't have as many amino acids. So with preparative size exclusion chromatography, what you could then do is you could take those fractions that came off and see where it came out, whereas on the UV chromatogram, since it's going through a UV detector after it comes off the column. And then you can collect the fractions that came together that have the protein of your interest and move forward with that. So typically then you would concentrate the protein again and add and then freeze it or however you want to store it. But if you were to run a gel of those samples, you would see that the peaks, the earlier peaks are going to correspond to bigger things and the later peaks are going to correspond to smaller things. And you'll see that this is different to how you would kind of see things on an SDS-PAGE gel, where the bigger things are traveling slower than the smaller things. And also remember that with SDS, you're unfolding everything. And so if you have a peak that is actually holds multiple things inside, then you're going to see multiple bands on your SDS-PAGE gel. But this brings us to the idea with the analytical size exclusion is that multiple proteins can be bind together, and this complex can actually travel together through this column. So you can imagine that if you have like a truck with a car on top of it, well, now this is going to be even bigger than the truck alone and way bigger than this little guy. And so you'll see this movement of the peak. It's often easier to see the disappearance of the smaller car or the smaller protein, the signal for the smaller protein, than it is to see the shift in the signal for the bigger protein. So often you're looking kind of for the disappearance of this peak, a shift of leftward shift of this peak, and increase in the height. And so this is why when you're doing this like analytical size exclusion chromatography, it's really important that you're loading equal amounts. And this is what, when we talk about when I get into the sample loop volumes, you want to inject like more than a loop volume so that you make sure that the loop is completely filled, not diluted at all. And so this way, if you see a disappearance of a peak, you're not like, well, is that because I didn't load as much protein? And so what you typically do with the analytical is, if you're doing it to measure, see if things bind, you would run them separately and then together, and you would be running equal amounts of each. This can be really helpful, but your complexes have to be stable enough to travel together. And so weaker complexes, they often will come apart and not be stable enough to move together. So if you don't see a shift in the peak, that doesn't necessarily mean that the proteins don't interact. They just don't interact stably enough to be detected with this method. A downside to this method is that you have to have enough it can take a lot of protein because you need to be injecting enough protein to get nice peaks, and you have to be like over injecting your loops. So that's another drawback, but it can be very useful for certain cases. You have what we call the void volume. This is the volume that's basically around all of the beads. And this is so anything that is too big to get into the beads. So this could be like an aggregate. If you have aggregated proteins, it's going to come off in the void that I'll show you later. That's going to be like the beginning fraction. It's going to be the quickest stuff, and it's going to come out first. And typically that's stuff that you don't want because it's going to be aggregated gunk that couldn't even get into any of the columns. Any of the pores. And so then you have the pore volume, which is the stuff inside. And then you have like the total column volume, which is the stuff inside and the stuff outside. And this is going to depend on the column that you are using.
Here are a few examples of columns. So the numbering system is, so like 10-300, that means that the internal diameter is 10 millimeters and the length is 300 millimeters. You might see for some of the older columns, so this one is like high load 1660, which is really, now they call these 16600, but this is in centimeters instead of millimeters, but then the diameter is still in millimeters, so it's kind of confusing. But basically this would be 16 of a diameter, so you can see it's a bigger diameter, and 600 centimeters, so it's longer. And so the longer the column is, the better like the resolution that you're going to get. So the separation between proteins of similar sizes. So you can see, and that's going to depend too on the diameter, which is also going to impact how much you can load, because it's going to impact the volume. And so if you're doing a typical like purification run, you don't want to exceed like 2% of the column volume. If you're doing analytical, then you want to go even lower to something more like 0.2% of the column volume. And you can see that the column volume for these analyticals is a lot narrow, it's a lot smaller. So one of these like these like 10-300, that is a column volume of about 23.5 milliliters, and that's including like all of the stuff inside and outside the pores. Whereas this big guy, this high load, it's like 120 milliliters. So it took me like 4 hours to equilibrate. So yeah, which is why it's kind of a pain to use, but it's nice when you get a nice peak. I'm sorry, but that's just gorgeous. I love it. That protein is like so well behaved. Not all proteins are like that, and the one I'm going to purify today, I'm sure that the peak won't be like that. But anyway, with this analytical one, you can see that here we have 3.2 by 300. So it's the same length as this bigger guy, this 10-300, except it has a smaller diameter, and so you're going to get a better resolution because the proteins, they're traveling through this column and they can't kind of like, you don't have this sideways movement, the sideways like diffusion of the particles as much, or the proteins as much, but they can kind of just have to go straight down. And so they're going to go straight down. They're traveling the same kind of bird's eye distance without having the back and forth sideways, if that made sense.
Your protein should not be coming off in the beginning of the run, the void volume, so the stuff that's just around it, and they should also not be coming out at the very, very end because your proteins aren't that small. But the good news for you is that means that you don't really have to wait that full 120 mils if you have one of those big columns for your protein to come off, although you still want to run like a couple column volumes when you're doing the equilibration and when you're doing the wash afterwards. So a typical run would go something like this. You would pre-equilibrate it with the buffer that you want. So typically I do 2 column volumes worth of pre-equilibration, and this is going to fill all of those pores with the buffer that you want. Then when things come through, the first part of it is going to be the void. So this is going to be anything that couldn't get into any of those pores, so the stuff that just traveled around. And so this is going to be the aggregate, and it's also going to be whatever was already in the column. And so that is now getting pushed out, that is now traveling out. So what like the pores are filled with. Then typically the first stuff you see is going to be some sort of like slight aggregations and stuff. So I have my method set so that it doesn't even collect the void, because if it's in the void, well, hopefully it's not in the void, but if it is in the void, then it's probably nothing that's useful to me. But then I see some slightly like clumpy stuff, probably like aggregate type of things. And then you see the bigger things come off and then the smaller things come off. And then later you get some sort of weird signal from like salts and stuff. But here you're looking at the 280 over the 280 and the 260. So looking at the contributions of like protein and nucleic acid, if you're interested in that sort of thing, you can do these on multiple wavelengths. And so, but the idea here is that now I was able to separate this bigger thing from this smaller thing. And so in this way, you're able to isolate the fraction, your protein of interest. And you can change the fraction size so that you are able to get a better definition. There's still going to be some cross-contamination between these peaks because this isn't like exact, and you still have some of both. But the better the resolution, the farther apart these peaks would be from one another. And this is going to depend on the column size, the column volume, and the column type. So the longer and or thinner the column, the finer the separation, and also the different types of resin. There are different like qualities of resin and different actual form makeups, chemical makeups of these resins. So let's talk about these. So a lot of columns are based on agarose, which is the same agarose that we use to make DNA gel. So like agarose gel electrophoresis to separate DNA by size. So this sugar agarose, and you make this agarose gel, kind of like mix itself up into the scarf, I like to think of it. And so this agarose is great for certifying things, especially if you cross-link it together, but it's not as good as some other materials like the sugar dextran, which is better for actually separating things. And so you'll often have different types of resin where you have some combination of sugars and different cross-linkers. For example, the type that I use the most is actually the Superdex, and this is a combination of dextran, so the sugar dextran, and cross-linked agarose. So you get the good separation properties of the dextran with the strengthening from the agarose. And although the agarose and the cross-linked agarose is strengthening things, these beads are still like jelly, like they are very sensitive to pressure, which is why you need to make sure that you set pressure limits on your column to make sure that you're not like squishing down the beads, which is not good, and it's also going to impact the resolution. Other types of resin include superose, which are based on cross-linked agarose, but without the dextran. Cefidex has dextran that's cross-linked with epichlorohydrin. So basically, when you're cross-linking, you're just kind of making links kind of between the different chains and that sort of thing. And then cefacryl is actually, this actually dextran that's cross-linked with a different thing. It's actually cross-linked with methylene bisacrylamide. And so bisacrylamide, you might remember, is actually what we use to help. This is actually what we use when we're doing an SDS-PAGE gel to make our gel polymerize. But here we're not polymerizing this, those acrylamide monomers. Instead, what we're doing is we're cross-linking this allyl dextran. These sugars are good because they're kind of pretty blah, but they're not, basically your protein isn't going to interact with them. Proteins aren't going to differentially interact with them, hopefully. So there's low non-specific interactions between your protein and the beads, because you don't want them to be sticking onto the beads. You just want them to be traveling through. And so you want it to be something that kind of like the environment that the protein's normally used to, that's just traveling around in all the time. And so this nice sugary gel is a good thing for that. The differences in the resin makeup also correspond to differences in the size of proteins that you're resolving. And so this is also going to depend on the pore size and that sort of thing. Basically, they have all these different formulations and variations. So in addition to the column sizes, they have differences in the size of the molecules that they're going to be good at separating. And so they have like charts where you can look and see, but remember that this is basically this MR. So this is the like relative molecular weight, but this is assuming that your protein is a nice like sphere, which proteins are not often nice spheres. But so this is the one I use the most, is Superdex 200 increase. And it's saying it's good for separating things that are 10 to the 4th Daltons. So about like 10 kilodaltons to about 100, 150 kilodaltons, if I did that math right. And if I want to do something smaller, then I typically use this like Superdex 75 increase. Sometimes you have a big range of things. So like superose is good for this if you have a range of protein sizes. You also see that there's like prep grade, and then there's like higher quality for better resolution. And I'm not exactly sure all of the various details between them, but you can check out their selection guides, which have some good information.
So we load by injecting into this injection port, and you thought only medical doctors got to use syringes. Nope, we get to use them too. And we're not injecting people, so we don't have to worry about hurting it, but we actually do have to worry about hurting it because this machine is super duper precious. And so you want to make sure, like, when you're injecting, that you're injecting straight in, you're not bending or breaking the needle in there, and that your needle is unclogged. So what I do before I actually load is I rinse the syringe. So I take it, I pull it out with like water and do a couple of rinses, make sure that you have a nice straight stream, there's no kinks in the needle. Then I do it in the buffer, so I do like 3 times in the buffer, and then I add my protein and I inject it in. We'll talk about the volume to inject, and then I inject like a tiny little bit more. I take a little buffer and inject a tiny little bit more to get any of the protein that was left in the needle. It's going to go now into one of these sample loops, and so we have loops of different size, so like 5 mils, 300 mils, 1 mil, and like 100 microliters. And then this sample loop is going to kind of store it for us until we're ready to put it on the column. So when we go to do an injection, what we're going to do is, instead we take this loop valve. So this is just the uniform software. This is Active Pure. And so if you go to the loop valve, so I put the loop position I want. Before you load it, you want to do like a loop wash. So I would do a loop wash of this, and it would wash this loop. Now when I want to do this, I'm in manual mode. So what this means is that when I'm, So if I'm doing, you can hover over the things and it'll see what you're going to do. So here it's saying that if I'm in, so it's showing that if I'm in manual mode, then they're going through, like I'm injecting it in, so that syringe port, and now it's going into the loop and then out to the waste. So this means that the loop is going to be filled with buffer before I inject. Then I'm going to inject, and it's going to push out the volume that I'm injecting. So if I'm injecting less than what the loop holds, then then you're not going to push out any of your sample. And so this is, if you want to make sure that you get all of your sample on, then you want to make sure that you are loading. So if you want to make sure that all of your sample gets loaded on, you want to make sure that you are loading about less than what the loop holds. And so typically you want to do less than half. This is because when you inject it in, a little bit is going to mix with the buffer that was in there and kind of like travel further. And so some might actually leave with the buffer, and like with a front, there's not a clear front between your protein sample and the buffer. And so if some of your protein gets into that buffer part that was in the beginning, it diffuses ahead, then you're going to lose it. If you're doing an analytical column, then what you want to do, or if you want like super great resolution, and you care less about the injection, you care less about the yield, then what you want to do is you want to inject more than a column volume. So you can inject like 1.5 to 2 column volumes. This way it's going to make sure that you push out all the buffer, and the loop is going to be completely filled with your sample. And this way you're going to inject equal amounts, and you're not going to have any dilution of the sample in there. But so you can see that the excess is going to waste. So if you inject more, it's just going to go out in the waste. It's not going to go onto your column. Then what I do is I bypass this before the run. And then during the run, what I'm going to do is I have my run set to equilibrate, and then there's like a step where it'll load. But typically what I do is I equilibrate beforehand, and then I go to execute manual instructions, and then I go next breakpoint. It's not on here because I'm not running a manual method. I'm not running a method right now, but I have a next breakpoint, and then I put next breakpoint, and then what's going to do is inject. So when it injects, what it's going to do is now it's going to change the subway route. So now it's going through the loop, but now it's going onto the column, and it's going to go onto the column, and then I have it set so that it would it would then flow some buffer through that line, so that anything that was in there would get out, and then it would go onto the column. Once it comes out of the column, then it's going to go through a UV detector. The UV detector is going to be before it goes into this fraction collector, and then the fraction collector is going to collect fractions of the size you tell it. I usually do like 0.5 or 1, but this is for the high load column, so these are like 1.75 mil, because this is like much bigger volume. Yeah, this is going to be a lot of concentrating to do. But you can see that these fractions are going to correspond, so I would collect the fractions that corresponded to the where the protein came out as detected by this UV chromatogram. You also notice that this protein is bound to nucleic acid, so this is why the 260 over 2 rate, there's like the 260 is way higher than the 280. And this is also, it's also a bit deceptive when you have nucleic acids, because this is going to make it look like there's more protein than there actually is, but there still is quite a bit of protein there. Okay, so I just injected, and so it's going through the column loop and on to the column. And then this is going to switch, and it's going to go from the buffer onto the column. So now it's going to go to bypass. Now that it did, so it did 3 mils like I told it to, and now it's going to bypassing the loop and going straight onto the column. Right now it's still going to the waste, but later it's, because right now it's just the void, but later it'll go to the fraction collector, and then I will hopefully have protein to collect. Okay, so protein is coming off the column. What you want to see is you're looking for a nice sharp peak that doesn't have, that has well resolution. If you see like shoulders and stuff, then there could be like contaminated proteins in there. And so you want to have a nice like symmetrical peak, and hopefully well separated from anything else. So in this run, you can see that there are clearly two different proteins, and at least, and you can see that they're separated. So we say we've resolved them, and so now I can collect the fractions that correspond to just the one I want, which is going to be this guy here. You also note that there's a little, the peak isn't quite clean, so there's probably a little stuff too that's making this not quite smooth. So we have these like glass Hamilton syringes in a variety of sizes, and so that's what I'm using right now. But if you have a larger volume, we just also have these tips that we can then screw on to just normal plastic ones.
When you're doing the run, you want to leave the syringe in there, but then after the run, you want to take that syringe and you're going to wash it. So I typically do like, I wash it a few times in water, and then I wash it in 70% ethanol. So like it's clean for the next person. You don't want things to get crusted on there. That could cause problems when someone tries to go to inject and then nothing comes out, which is another reason why I make sure beforehand that the needle's right. And then also you don't want things kind of getting pushed, like getting into the injection valve. We had problems with that before. And then people we were losing sample because our needle wasn't actually going in all the way. And so the sample was kind of like flowing out around. So that wasn't good. You also then want to wash your columns, wash your loops, just like we did before the run. So you just do a loop wash like that. And those are just a couple things to remember. And then you, of course, wash your column with water or whatever your storage buffer is in order to clean it up for the next person and get ready for so that then you can then equilibrate it for the next run. When you are doing your equilibration, often I do the equilibration manually. And so when you have a method, I have my method set so that it knows what column it's using. And so it will set the pressure limits. But when you're doing them manually, you need to make sure that you set the pressure limits. So in order to do this, you can go to manual, execute manual instructions, and then alarms. And then you have the pre-column pressure, so going onto the column, then the delta column pressure, so the difference between the top and the bottom, kind of, so if things are getting stuck in here. You want to have these pressure limits so that you're not squishing down all of those beads. And so how do you know what to set them? You can go to this column handling, and here you have information about all of the different column types. So if I were to go to my SuperDex 200, my go-to, so my go-to is this like SuperDex 200 increase 10 300 GL. And so basically this is saying that this increases this newer formula. I mean, not that new, but 910-300. So a 10 millimeter internal diameter, 300 millimeter length, and glass casing. And so you can see that the maximum pre-pressure column limit is 5, and then the maximum delta is 2.6. It also has like a maximum flow rate of 1.8 mils per minute, but that if you run it that fast, you're not going to have good separation probably, at least for the bigger things. And then if you have, it's also probably not going to let you, because it's going to make the limit the pressure too high. When you're running it in the cold, like we do in our deli fridge, then you actually want to run it at an even lower rate. But so if your column is really clogged, then you're going to have pressure problems, and you'll have to decrease the flow rate even more. Some of the columns I had to use at like 0.5 mils per minute. And so this also tells you the column volume and various parameters. And then you would see that there are different ones. So this high load that I'm using, it has 120 is column volume, and it's a 0.5 and 0.3 for the pressure limits, 1 and 1.6 for the flow rate stuff. In terms of the flow rate, if you have a bigger protein, if you lower the flow rate, you're going to get better resolution, because it's going to give the smaller things more time to travel in and out of the pores. And therefore, it's going to basically give them more chances to separate themselves from the big guys. But you might get, if you go too fast, you'll get, I mean, if you go too slow, you could get poorer resolution of the little guys. And because you're giving them so much time, that they're kind of diffusing around more and that sort of thing. So when I did like one of those 10-300s, I'm normally running it for the SuperDex 200, 10-300. I'm normally doing it at like 0.6 to 0.8 mils per minute. And then that big guy that I did yesterday, I did at like 1.2 mils per minute. It's also going to depend on the different resin types. So if I have, for example, the SuperDex 75, same column size and everything, but here I have different pressure limits and different flow rate recommendations and that sort of thing. So you want to make sure that you set those alarms before you actually put things onto the column. Typically what I do is I then set a timer, and I set it to like 2 column volumes worth. And so you want to make sure that you set it to volume instead of time, unless you have calculated it out to do in time. And then the other thing you want to do is you want to make this action, you want to put end, then you insert and execute it. You want it to end when it's done, probably, so you don't forget about it, and then the system stays on and it's like wait mode, and then it burns out the light lamps and stuff. So don't do that. And of course, you want to make sure that you have it going to the right column when you are doing this. So you would set position, and then it would go down the column. So my typical run methods, this is for that like SuperDex 200, the 10-300. So they have like default one methods that you can find, then you can change them how you want. So I like doing for my start protocol, I like having it do this variable list, which is then going to allow me to change things like the column position and the sample place, instead of just doing it manually here. And then it also asks me for my result name and location. And then there are other things you can do if you want that. So you have the column position, it sets the limits, which is great. And I'm going to do things in terms of column volumes. So I have my method base unit as column volume. Equilibration, so it's set to do like this full equilibration, but typically I pre-equilibrate it, and then I start the run, and then I do my injection, and then I inject the sample. I just do a next breakpoint, as I'll show you, to get to the next, to get it to inject. But it's going to then do the sample application. And for the sample application, here I'm telling it what loop I want it to go from, but if I have it in my methods where I have the variable list, I can then change this when I go to start the run. So I have it set to the loop position and then empty loop. So basically after, it'll send the buffer through to wash the loop out. And then it goes on to the elution. So getting when the protein is coming off. The elution is going to be isocratic, which means that it's a single buffer. And so it's going to do one column volume. And so it's going to then collect things in a 96 well plate. This is going to, I have it to set start fractionation after 0.25 column volumes. So this is basically saying don't collect the void volume, so the stuff that's outside of the beads. So I know I've been talking a lot about this Cytiva guidebooks and stuff. They have a lot of really great resources. If you're having problems, like, I mean, they're just like experts at this, and I literally am not paid by them or anything. They're not telling me to say any of this. But I do find that they have some really nice resources, especially if you're having some problems. So they're often, you can have problems with, you have like poor resolution. You can also have, so the protein peaks aren't separating well. You can also have problems where your peaks look funny. This can be caused by if the column pressure is weird. So one of the things is if your protein is too concentrated and it gets really viscous, then it can actually like overpressure the column. And then you can also have problems where there's like the column pressure is too low, like there's, and then there's problems with that. And they have like a troubleshooting guide, as well as this whole like guidebook. This will help you like choose your column and optimize various things. So if you want more information, I recommend that you check out these guidebooks, and they'll give you a lot more information, probably more information than you will want. But it probably has what you're looking for, and you can see all these different columns with their different ranges and sample capacities. So typically, if you're doing like an analytical, they recommend like 0.3 to 0.5% of the bed volume. For purification and stuff, if you want high resolution separation, then you don't want to do more than like 2% of your column volume. But you can go higher but you can go higher if you don't care as much about, but you don't want to do more than 30% of the total volume. Sometimes if you have one of the bigger volumes, basically they have some columns that are like kind of shorter and squatter, and that you use those for like desalting. And there you don't care so much about resolution. You just want to make sure that your big things and your really, really small things are going to be separated.